Hello friends, welcome to this session where we will be exploring count regressions using R. Count regressions are statistical models specifically designed to handle count data, that is data where the outcome is a count, such as the number of times an event occurs. You might encounter count data in a variety of real-world scenarios like tracking the number of insects on a plant, the number of car accidents at an intersection, or even the number of patients admitted to a hospital. These situations can't be modeled effectively with standard linear regression, which assumes a continuous outcome. Instead, count regressions come to the rescue with models like Poisson, negative binomial, quasi-Poisson, zero-inflated models, and hurdle models, which we will explore today. In this video, I will walk you through how to perform these types of regressions using R programming and show you how to interpret the results effectively. So, let's get started into count regressions. Before we start into count regression, let's first compare it with more commonly used linear and non-linear regression models. Linear and non-linear regression models typically deal with continuous response variables, things like height, weight, or temperature, where the outcome can take on any value. These models assume that the residuals or the differences between the observed and predicted values are normally distributed and that the variance of the errors is constant, a property known as homoscedasticity. Commonly, linear regression uses methods like ordinary least squares to estimate the parameters of the model. Now, count regression is different because it deals with discrete count data, values that are whole numbers like the number of times something happens. For instance, the number of insects on a leaf, accidents at an intersection, or patients admitted in a hospital ward. Unlike linear regression, count regression models assume either a Poisson or negative binomial distribution depending on the data characteristics. These models are especially useful when the data shows overdispersion, meaning the variance exceeds the mean. Count regression models can handle this overdispersion or even skewed data far better than linear regression models. Now, let's take a closer look at the key differences between count regression and linear or non-linear regression. Firstly, the data type. In linear or non-linear regression, the response variable is continuous. For example, we might be predicting something like height or weight, where the values can take any number including decimals. In count regression, the response variable is discrete and represents counts. These are whole numbers like the number of accidents, number of hospital admissions, or the number of insects on a plant. Next, the distribution assumption. Linear or non-linear regression assumes that the residuals or the errors in prediction follow a normal distribution. In contrast, count regression assumes either a Poisson or negative binomial distribution depending on the characteristics of the data. Finally, the variance assumption. In linear regression, the model assumes constant variance, meaning the spread of the residuals remain consistent across all of the predictor. This is called homoscedasticity. On the other hand, count regression handles cases where the variance increases with the mean. This phenomena is called as overdispersion, where the variance is greater than the mean. And on the right hand side of the slide, you can see the fits for three models. The top plot shows linear regression fit where outcome variable is continuous variable. The middle plot shows Poisson regression fit, which is designed for count data but assumes the variance equals the mean. The bottom plot is a negative binomial regression fit which better handles overdispersed data where the variance exceeds the mean. Now that we have discussed the differences between linear and count regression, let's briefly cover the types of count regression models. Poisson regression is used when the mean equals the variance. Negative binomial regression handles cases of overdispersion where the variance is greater than the mean. Zero-inflated models are used when there are excess zeros in the data and model two processes, one for whether the event occurs and another for the count. Whether the event occurs generally modeled using the logistic regression. And similarly, hurdle models are there, also handle excess zeros but work slightly different by separating non-occurrence from the count process. In zero-inflated, we separate occurrence, and here in hurdle models, we separate non-occurrence of the event. And each of these models are is designed to to address specific characteristics in count data, making them powerful tools for prediction. To explore count regressions, we are going to use the insect sprays dataset, which is bundled with R. Let's first take a look at the structure and summary of the dataset. It contains 72 observations and 2 variables. The first variable is count, which records the number of insects counted after applying a particular spray. The second variable is spray, which indicates the type of insecticide spray used. There are 6 different sprays labeled from A to F. And when we see the summary, the count variable ranges from 0 to 26 insects with a median count of 7 and a mean of 9.5. Each spray has 12 observations, and we want to see how effective each spray is in reducing the insect count. To understand the relationship between the count of insects and the spray used, let's visualize the data using a box plot. Let's visualize the relationship. For that, we'll require the library ggplot2. And we'll plot a box plot for that, and ggplot is the function and data is insect sprays. Aesthetic mapping, spray is the x-axis and y will be the count of that, and fill I will map to the spray. That's not necessary also, but we'll do that, spray. And then geom box plot we are going to use to visualize that. And here we can see that these 3 sprays A, B and F are similar to each other. There is no statistically significant difference. It appears that from the visualization. And these 3 sprays forms a different group, that C, D, E. Those are similar to each other. We'll confirm that by performing ANOVA. ANOVA may not be the best one because we have not seen the distribution or that. We assume here that the distribution may be normal, and for that we are going to use ANOVA mod AOV, and that require the formula first, and count is the outcome variable and spray will determine that count. Insect spray is the data set, and we'll run that ANOVA and we'll see the summary of that, summary ANOVA, so that we can see the significance levels also. And here we can see that sprays are responsible for the variations, are statistically significant differences are there between the different sprays or counts because of the different sprays. We can use the 2K HST also. Here I want to use 2K HST on the mod object and run that. You can see that pairwise also A, B, C. If you explore that A, this is for F and A, and this is for F and B. These 3 are similar to each other. No statistical significant difference between the pairwise combinations of these 3. And if you explore for DC and this EC also, you can see that, and here also that E and D is there. These 3 form a different group where statistically significant difference is not there between the pairs of these 3. Let's move further. If you don't want to use this ANOVA, you can use Kruskal values also. I will do that here only on the plot using library ggpub_r, and here just we have to add one geom, that is stat compare means, and the Kruskal values result will be there on the plot. Here also there is significant difference between the sprays counts because of the sprays, because p value is 1.5 into 10 raised to minus 10, quite less than 0.05. Now we will fit different regressions, count regressions to this data, and the first count regression we are going to fit is Poisson model, and for that we'll save the model results into object called as Poisson, and we'll define the model now, and for that we are going to use GLM model, that is generalized linear model, and first argument is the formula, and that formula is count, that is our outcome variable, determined by the predictor variable, that is spray, and data is insect sprays, and family for this regression we have to define as Poisson, and by default it will take link function as log function, and we'll run that and we'll see summary of this model, summary Poisson, and when we run that we see the summary. Here call is there, that formula and all that which we have used to fit the Poisson model, and these coefficients are there. These estimates are the actual effects of the different sprays. The first spray A is used as a reference spray, and then second is the spray B. This is the effect of spray B, effect of spray C in comparison to effect A. All these coefficients are in comparison to the reference category, that is A. And here we can see that there is significant effect of spray A on the insect count. Spray B, if you compare the effect of spray B with spray A, that is not statistically significantly different. Spray C is significant, effect of spray C is significantly different than spray A. Likewise for spray D is also effect is statistically significantly different. E also significantly different, and spray F is not statistically significantly different than the category A. If we want to calculate actual insect count because of spray A, we have to exponentiate this effect of A to get the insect count 2.67. That is, we'll run that, and okay, I forgot that exponential exp, and then we have to put that 2.67415 in the bracket to exponentiate that. That is around 14.5. Means when we apply insect A, mean number of insects on the plants are 14.5. When we do that for coefficient B, spray B, then spray B will have, I will exponentiate that, spray B will have this is not, we have to get the difference of these two, effect of A and effect of E, log this one. We'll run that. For spray B, 13.7 insects, not much different than the 14. For spray C, I will copy this, and A will keep that. This log effect I will take here, and when we run that, no, that 2 negative came to be positive. I will remove that and run that. That approximately 2 insects will be there because of spray when we spray C. And similarly we can do for all those different sprays. For spray D also negative, that is around 2 only will be there for spray D, and again the 2 negative came together. When run that, 4.91 insects will be there because of spray D. Spray D is less effective as compared to spray C, little less effective, but not statistically significantly different. For spray E, I will not repeat that double negative error again. For spray E, 3.5 insects will be there, and for spray F, we'll have to subtract that from the effect of spray A, and when we run that, 3.49 for spray F, no, for spray F this value is required, and this will run that, and 12 insects will be there. As we can see from this model also, these 3 sprays are more effective as compared to A, B and F in controlling the insect counts, and out of that C is more effective as compared to D and E in controlling the insect count, but there is statistically not significant difference between these 3 sprays, and but we have to confirm that whether the difference is statistically significant or not, because medians are different. Please note the AIC value or Akaike information criteria value for the Poisson model, and that is 376.59. This AIC value will use to compare the different models, which model is better. We determine by using this AIC value. The next model which we are going to fit is negative binomial model, and for this model we have to require this. I typed in console, I will bring that to script, and we require library mass. And if you have not installed this library mass, you can install that through tools, install packages, and when that dialog box appear, type in mass there, and the select from the drop down list, click install, package will get installed. I will not install again as I have installed it. And the next is neg binom object I will create for this model, and glm dot nb from mass we are going to use here, and same formula interface we are going to use, but this time family Poisson we don't require because this negative binomial is there in the function name only. We'll run that, and now we'll see summary of this model, summary neg binom, and we'll run that. And as you will see here, this AIC value is 374.22, and for this AIC value is 376.59. This little less value it is, therefore negative binomial appears to be better fit as compared to Poisson, and the effects are similar as we have seen for the Poisson model. All the coefficients and all those are similar for the negative binomial also. Though the insect spread data is not zero inflated, we'll learn how to fit zero inflated model here. And to fit zero inflated model, we have to call library PSCL, and when we run that, the library is there. I have installed that, and if you are not installed, then you can install the PSCL using this install package menu. Now we'll fit the model, and there are two types to model the occurrence of zero. Occurrence of zero will be modeled using logistic regression, but occurrence of events or those count data is modeled using first by zero inflation model Poisson I will use, and for that the same formula we are going to use, but I'll put that there, mod Poisson, zero inflated Poisson object I am going to use this assignment symbol, and here we'll require the function as zero inflated, and count spray here will require this rod symbol and 1 to account for the different model for the count data, for the zero data. Here we will require distribution to declare, and that is Poisson, and we will run that, and we'll see summary of this zero inflated model zi underscore Poisson, and we'll run that. Spelling mistake is there in this summary, and run that. Now the summary is there. Again the coefficients are similar. When do that, and there shall be 2. This is for Poisson and this is for zero inflation model coefficients. That is binomial one, that is for those zeros, and probability 0.637 means those zeros are not significant. Count of 0 is not significant and distribution of 0 is not different. We conclude that, and here AIC value has not been calculated for this model, but as this is not zero inflated, we cannot use this model for fitting that. We'll go for the another version of that, that is Z neg binom, where we convert this to neg binom, and we'll run that. Neg bin is the correct option. I will run that, and run that. NaNs are produced for square roots, and that because that is not actually zero inflated one. We'll see the effect again. The counts are modeled using the negative binomial one, and zeros are counted using different one, and the similar results are there in the zero inflated model with negative binom also. And now the last model which we are going to fit is the hurdle model, and hurdle model is used when the event occurs only when it overcomes a certain hurdle, and because of hurdle, zeros will be there. When hurdle is overcome, count will be there. Therefore, count follows a different distribution as compared to those zeros, and counts are processed using the Poisson event, and zeros are processed using the binomial model. And for that, we are going to use hurdle function from the zero inflation model only, not hurdle function from the PSCL model. I am copying this code and appropriating that code for hurdle model. I will put that hurd here, and hurdle is the function hurdle. This one is not required for us, and this distribution is also not required for us. This is sufficient. When we run that, the model gets fitted, and summary of hurd we'll see. The Poisson counterpart is the same one as the Poisson model, and this is for zero hurdle coefficient. It's a binomial model with a log-link function, and here also the zeros doesn't have any significant, those sprays doesn't have any significant effect on those zeros. Therefore, this hurdle model is also not good model to fit to this data, and that we have fitted all of that. Quasi-Poisson we have not fitted here, but quasi-Poisson actually doesn't assume any particular distribution while fitting the model. And that's all for this session. If you are like this video, please click the like button. Subscribe to my channel if you are not subscribed yet, and click notification button to get notifications of my new videos. Thanks for watching.